let's move on to the next talk. Next two talks are stars of all-time favorites, 1915 and Hercules X1. First, we will hear from Brianna Mills about the new spin measurements of GRS 1915. Yes, Brianna, that's yours.
Sorry, I tried to unmute myself. Hello. Hi, I am Brianna. I'm a graduate student at the University of Virginia, working with Shane Davis. And I recently just got done working on GRS 1915, a really interesting source, as many of you already know. So today I wanted to revisit the topic of the spin of the black hole in 1915. So just to give you a little outline, first I wanted to mention the previous black hole spin estimates for 1915, and then I'm going to focus specifically on two spin results, one from Middleton et al. And one from McClintock et al., because they both use the same method to get at the spin of 1915, yet they arrive at two very different spin estimates. So I wanted to talk about that discrepancy a bit, and then revisit that conversation with new constraints on the mass distance and inclination since those papers were published. And then I'll finish with the impact that the parameter uncertainties in mass distance and inclination have on estimating the spin, particularly for 1915. So there are a couple of different ways to get at the spin of a black hole. And for 1915 specifically, this has been done a lot. So for modeling the relativistic iron K-alpha line method, this is the broadened reflection spectrum from the corona irradiating the accretion disk. And if you model that, the spins for GRS 1915 are typically very high. It tends to favor high spins for this method, whereas the QPO method, modeling the power density spectra, seems to favor lower spins than the iron K-alpha line method, from about 0.7 to 0.9 for the spin. And the spin that I'm talking about here is the dimensionless spin parameter, which EXTP would probably help really well with the QPO method and the relativistic iron line method. So we could probably constrain those maybe even more. But for this talk, I'm going to focus on the continuum fitting method, which is the one that I'm most familiar with, and is the one that these two groups had discrepant spins with. So the continuum fitting method is ideally you want a disk dominated spectrum to fit with a disk accretion disk model that's typically modeled after the Shakura-Sunyaev thin disk model. And doing this, you can get at the location of the innermost stable circular orbit, which would then give you a spin. So that is the method that they used. They also use very similar models to model the accretion disk, as well as the hard X-ray coronal component, yet they arrive at two very different spins. And the reason for this discrepancy is not due to the continuum fitting method itself, nor the models that they used. It's largely due to their data selection. As most of you already know, GRS 1915 was very, very variable. It's very difficult to talk about the variability of GRS 1915, let alone get a disk-dominated spectrum. So that's the challenge that these two groups faced when getting data selection criteria for 1915. And now GRS 1915 is in quiescence. So I guess it's not so variable anymore. But at the time, these two groups chose different data selections. They actually have different variability classes that they use to select their data. And the biggest differences are that the Middleton et al. Data selections are varied in luminosity from 30% the Eddington luminosity all the way to 90% the Eddington luminosity. And the McClintock et al. Observations specifically chose observations that were less than or at 30% the Eddington luminosity, so that you don't run into this problem of the underlying assumptions in the accretion disk models breaking down as you go to higher and higher luminosities. Because at that point, you might be reaching a region where you have a thick disk and not necessarily a thin disk anymore. So both of these papers came out around the same time. They also talk about each other in their papers, which I thought was also really interesting. So you can read more about what they have to say about each other and their own data selections if you haven't already. But the takeaway here is that they use the same method, same continuum fitting method, but they have different observations. And that is the reason for the discrepancy here in spin. So I wanted to look at these spins again now that we have better constraints on the mass, distance, and inclination to GRS. So at the time that these papers were published, the mass was about 14 solar masses, distance around 11 to 12 kiloparsecs, and a disk inclination of about 66 degrees. So then 8 years later, Reed et al., based on really impressive VLBI parallax measurements and constraining the superluminal jet motions, were able to get better constraints on the mass, distance, and inclination. The most notable one is that the distance is now a lot closer at about 8.6 kiloparsecs. And this, all three of these parameters will impact the spin, but most notably, we find that the distance does. So using these new constraints, I first started with redoing the Middleton et al. Data analysis. So I used PH-spec to model the disk emission, which is what they also used, and also used Simple to measure the contribution from the corona. And we found that the spin for this data set in particular wanted to be pushed up from about 0.7 to about 0.86 is what we get here. And so the fact that the spin wanted to push up caused a little bit of concern for the McClintock et al. Data set, which was already at near maximal spin even before these new constraints on the mass, distance, and inclination were published. So we find that for the McClintock et al. Data set, it wanted to push above this maximum limit. And we find that's true for the best fit if you use the 8.6, all the other values for the mass, distance, inclination. However, if we allow for some wiggle room in the mass, distance, and inclination, we get a range of spins that are acceptable for the McClintock et al. Data set. Oh, I think I'm freezing here. Oops. Okay, hopefully I'm okay now. Just froze for a bit. So for the McClintock et al. Data set, we find that if the distance to GRS is above 10 kiloparsecs, then we can get a reasonable fit to their data set, and we get a range of spins from 0.9 to 0.99. So this plot that I'm showing here is a distance in the upper left, mass in the upper right, inclination in the lower left, and a histogram of the spins from the resulting combination of those three in the bottom right. So in particular for the distance plot in the top left, the blue points here are reasonable fits that we get within a 99% confidence, and the red fits are fits that do not meet the 99% confidence. So we see that above 10 kiloparsecs is where we get most of the good fits for the McClintock et al. Data set, which gives a range of spins from 0.9 to 0.99. Doing the same analysis, allowing some wiggle room for the mass, distance, and inclination for the Middleton et al. Data set, we find that we have a very broad range of spins allowed for GRS. So our best fit spin is about 0.86, which is fairly moderate. In the past, I think most people preferred to say that GRS was a maximally rotating black hole, but our results suggest that perhaps it could be moderate. It's still a possibility that it's moderate. And in fact, the spin can be anywhere from 0.4 to 0.99 based on our analysis here. So in conclusion, so I talked about the Middleton et al. And McClintock et al. Data sets. They both got discrepant spins, but it's largely due to their data selection. And so when considering the new mass, distance, and inclination that was published after their papers, we find that the spins wanted to push up. So now the Middleton et al. Spin went from 0.7 to about 0.86, and we get a broad range of acceptable spins if you allow for wiggle room in the mass, distance, and inclination. And for the McClintock et al., excuse me, McClintock et al. Data set, we find that if the distance to GRS is greater than 10 kiloparsecs, then we get a range of acceptable spins from 0.9 to 0.99. So this suggests that we still need even tighter constraints on the mass distance and inclination if we want to narrow down the spin of GRS 1915. And with that, I'll stop there. Thank you.
Thank you so much.